Okay, so on this problem, our picture is as follows. Um, you got some line, and then some other line here that is, maybe under it or something like that. Right? And not parallel. In fact, you can check without too much trouble that. So by the way, we know I'm going to call that point x1 and this direction vector here v1. And you can interpret those from the given parameterization. And then there's an x2 and a direction vector v2. Okay, so we're looking for this plane that's kind of equidistant from both and parallel to both. Okay. So now you probably already figured out how to find the normal vector, right? Are you okay with that?
Yes.
Yeah, so the idea there, let me just repeat, the way you find the normal vector is, well, it needs to be perpendicular to the plane, and yeah, we're going to use a cross product, because if it's perpendicular to the plane, and if the plane is parallel to both of these, then n has to be perpendicular to both of these, so we'll just use v1 cross v2.
Can you,
Yeah.
sorry, because they were talking about some midpoint thing.
Yeah. So the hint, well, the midpoint thing is about how you find sort of x naught. Now we need to find a point in this plane.
Because these lines like this?
Yes.
Okay.
Yeah, they're not parallel and they don't intersect.
So, but can't this point in between these two lines, can't that be? Oh, never mind. That is. Okay, that's how you do it.
Okay. Yep. So yeah. So how to find some point that's in the plane, and what the hint says is pick any point on each of these lines. And by the way, we have some sort of given to us, right? I mean, sort of the base points for these parameterizations. And the hint suggests that the midpoint must be on the desired plane. So if I look at this line segment between those and look at the midpoint of that line segment, I'm going to call that x naught. I claim x naught has to be on that plane. And here's why. What if I were to, I'm going to form a couple of, the problem says similar triangles, so let's do that. I'm going to drop a perpendicular from this point here down to the plane.
Is that line going down? Like, is that like going?
Yeah, dropping a perpendicular means this is going to be perpendicular to the plane. It might not be straight down, depends on the angle of the plane.
Sorry, I meant the solid line you drew.
Oh, this line here.
Yes.
No, that's just a line segment connecting this point on this line and this point on this line.
Right, and is it going like straight down to the line?
No, it's going from this point to that point. It might not be straight. It might not be it might not be vertical. Yeah, because this point could be over here, as far as we know. Yeah, and by the way, I mean straight up and straight down don't really matter in this problem. This is kind of, in other words, same problem. Okay. Right. There's one advantage to this over a chalkboard, by the way, is you can't do this on a chalkboard. Or you can, but it's a lot harder. Anyway. Okay, so we dropped a little perpendicular there, and then likewise, let's drop a perpendicular over here. So I've got two similar triangles now. I claim they're similar triangles. In fact, they're, what do they call them, congruent triangles. Clearly, that angle is the same as that angle, and that angle is the same as that angle, and that's a right angle, and that's a right angle. The angles are all equal. And by assumption, this plane is equidistant from the two lines, which means that this, by assumption, is equal to that. And therefore, these other lines are of equal length. So in particular, that distance is equal to that distance, which is how we came up with choosing this point. In fact, we probably should have gone the other direction. I probably should have said, well, by assumption, I'm taking the midpoint, so that distance is equal to that distance. And if those two distances are equal, then these triangles are congruent, and therefore those distances are equal, and so therefore these points are equidistant, or these lines are equidistant from this plane. So anyway, that's the argument that justifies that this works. But this formula x naught is just the average of x1 and x2. That gives you your x naught for the plane, and then it's just n dot x equals n dot x naught. Make sense?
Yeah.
Questions, anybody? Everybody happy?
Could you just explain, like, after you got the perpendicular line, like you took this point of it, like just those two, I guess, right angle, the object.
Talking about this right angle and that right angle?
Yeah, just explain, like, after that, what you got.
So how do I know? You're asking like what was my discussion of the triangles?
Yeah, please.
Yeah, sure. So the idea was, and I kind of said it backwards the very first time I said it, but by assumption, and let me draw this picture a little bigger over here because it's sort of awkwardly small there. So this was our x2, and this is our x1, and this is our x naught, which we defined to be halfway in between those. So I know that that distance and that distance are the same, and that's a right angle and that's a right angle, and these two things are parallel, which makes that angle equal to that angle. And then by subtraction, that means that that angle is equal to that angle. So these are clearly similar triangles. And in fact, furthermore, not only the similar triangles because all the angles are equal, but that length is equal to that length, and therefore that length is equal to that length. So if you think about what these two distances are here, these two distances are, on the one hand, the distance from that line to the plane, and this one here is a distance from that line to the plane. So these two distances being equal means that the plane is equidistant from the two lines. So that's why I put that hint in there. I mean, it is hard to come up with, well, finding that x naught and knowing, what x naught to pick. I mean, some students try to find maybe, the point on this line that's the closest to this line, and vice versa, find the point on that line that's the closest to that line, and then take the midpoint of those. And yeah, that would work, but it's just what the clever observation is that you don't need to find the closest. This doesn't need to be a right angle, and this doesn't need to be a right angle. All you need is just a midpoint between any 2 points on the 2 lines, and then make a similar triangle argument. So, okay, let me stop the recording here.